this example right here. So standard reduction potentials for the half reaction in single-use alkaline batteries. So that's like your Duracell or your Energizer battery, your AA or your AAA, but single-use, not rechargeable. There is actually different chemistry going on for the rechargeable batteries, okay? So but our alkaline batteries are called as such because we see the production of hydroxide in these half reactions. So that's why these are called alkaline batteries, right? Because they're basic. So here we have our two half reactions, and in these types of, real practical electrolytic cells, or excuse me, actually the voltaic cells, the reactions are much more complicated. They're not as straightforward as those nice simple reactions we've been looking at. For example, zinc oxide solid plus liquid water plus 2 electrons makes more zinc solid, right? So it's a solid-solid reaction, which we haven't seen before, okay? So what is the net ionic equation for the cell reaction and the value of E cell? Well, I'm going to show you two ways to do this, okay? So we remember that E cell is E cathode, I'll just say E cath minus E anode, okay? And if I stare at these and remembering that I want E cell to be positive and maximum value, right? Then, if I flip this one, the negative 0.15, I have a negative plus a negative to give me a negative. That's no good. But if I flip this zinc half reaction to become an oxidation potential, that's going to make that positive. And when I add a positive and a positive together, I get a positive number. So if I was good at just recognizing that, then the way I could do this calculation would be cathode minus anode. So that would be 0.15 volts minus, and I subtract it as a reduction potential. So it's going to be minus 1.25 volts, which equals positive 1.40 volts. Okay, so that gives us the cell potential right away. And if you've ever put a little voltmeter on one of your AA batteries, they're about 1.4 volts or so. You get about that much out of a full charge of one of those batteries. Okay, so do that. I would encourage you to, if you have a voltmeter handy, put the two leads between your positive and negative end of the battery and see how much juice it has in it. Okay, so but how could we do this via the net ionic equations? Because this is also asking us to get a net ionic equation out of this. Okay, well, we recognize we're going to leave the cathode reaction as is, which is going to be this manganese half. So let's write all of that out. Try to write it a little bit carefully so it's not as sloppy. And again, this is another, not straightforward reaction in these little battery cells, right? Consider you've got to do some very novel things to get that reaction to go in those tiny little batteries, okay? And we didn't change it, so that's 0.15 volts. So now I want to flip this one, and you notice they're both 2 electron processes, so that's great. I don't have to multiply, by any numbers or anything like that. So I'm just going to flip that reaction, 2OH minus plus zinc solid, and now that makes zinc oxide and some liquid water and my 2 electrons. And of course, I flip the reaction, so I flip the sign of the cell potential. And now, of course, you can see when we add those together, that's going to give me my 1.40 volts that I came up with before. And now this helps me get the balanced reaction. So you can see the hydroxides cancel, and the electrons cancel, and the water cancels. So this actually isn't too bad for the overall net ionic equation. 2MnO2 solid, okay, plus zinc solid, and that makes zinc oxide and this manganese oxide compound, okay? And I could even use this net ionic reaction to get my simple cell line notation, Okay, so I remembered that here now my zinc reaction was the anode and the manganese reaction was the cathode. So when I do my line notation, I start with the anode, and in this case, that's zinc solid going to zinc oxide. So I would say zinc, and I'll drop the phases just to make this a little bit easier. Zinc to zinc solid, and then double line for the salt bridge or the porous bridge. And then now that's MnO2 goes to Mn2O3. So that becomes very useful and practical to write that cell notation. Okay. So I think that I have, do I have another example? Yes. So I have another example, and I'll record that in a part C video.